let's start discussing this quiz. So first and foremost, we're asked to indicate the number of protons, neutrons, and electrons in each atom or ion. Okay, so first and foremost, we're looking at zinc 2 plus 65. So in order to figure out our number of protons, we're going to need to consult the periodic table. So our number of protons, if we go to the periodic table and we find zinc in the periodic table, we see what is zinc's atomic number? 30. Okay, so with the atomic number established, we know that our number of protons is equal to 30, which is our atomic number. Okay, the next step in this process, we're going to talk a little bit about the mass number. What does this mass number allow us to calculate? Neutrons. So then our number of neutrons is equal to our mass number minus the number of protons. So then our number of neutrons is equal to 65 minus 30, which gives us 35 neutrons. Does that make sense to everyone? Our final step is to calculate our number of electrons. And to calculate the number of electrons, we're going to need to use the charge and our number of protons. So our number of electrons is equal to our number of protons, which is 30, minus the charge. And what is our charge? What's the magnitude? Yep, 2 plus. So we're subtracting 2, and that gives us a total of 28 electrons that this given ion has. Does that make sense to everyone? Okay, so let's now tackle this iodine isotope. So in this case, let's switch to a new pen color. We're dealing with iodine 127 minus. So just like with zinc, we're going to go to the periodic table. So for iodine, what is iodine's atomic number? 53. So how many protons does iodine have? 53. So let's write that down. So for our number of protons is equal to 53. Let's now calculate our number of neutrons. Our number of neutrons is equal to our mass number. And what is our mass number in this case? 127. Okay, minus the number of protons, which is 53. That gives us, for our number of neutrons, a total of 74 neutrons. Does that make sense so far to everyone? Okay. Next, what we're going to do is we're going to calculate the number of electrons. And to calculate the number of electrons, we take our number of protons, which is 53, minus the charge. And what is the charge of this ion? -1. And when we subtract a negative, that's the same thing as adding a positive number. So that gives us 54 electrons to work with. Does that make sense so far? You should be comfortable seeing examples similar to this on your tests. Okay, now the second problem is a little more bulky. We did an example of this at the end of last lecture. So let's dissect this problem. Lithium has 2 major isotopes. Lithium 7 has a mass of 7.01600 AMU and a percent abundance of 92.41. So our mass is going to be equal to 7.016003437, and our percent abundance is going to be equal to 92.41%. Okay, so that's our first isotope. Now for lithium 6, let's write down the mass and the percent abundance. So in this case, the mass is 5.998 AMU, and the percent abundance is 7.59%, just reading off from the word problem. Now, we are asked to calculate the average atomic mass of lithium. Yes? It should be on the other side. Yeah. Yeah. Mm-hmm. So Once we have this information established, do we have all the pieces that we need to calculate the average atomic mass, which is the weighted average of all isotopes? Yep. So to do that, if we want to calculate the average mass, all we have to do is take the mass of one of our isotopes, in this case, 7.016003437 AMU, times its percent abundance, which is 92.41%, divided by 100. We've accounted for one of our isotopes. Do we still need to account for our second isotope in this weighted average? Yes. So to do that, we'll add 5.998 AMU times the percent abundance of 7.59% divided by 100. And that gives us an average mass. Let's now enter it into our calculator. So let's open up the presenter. One moment, let me pull up the presenter. Let me pull up the presenter, and if you, during this time, please get out your calculator. Okay, here we go. So now with our calculators ready, let's now input each of the components of our calculation. So first and foremost, we're going to enter our mass, which is 7.0016003437. Okay, so we have this number entered. What type of operation are we doing next? So looking at our equation, what are we multiplying this by? 92.41, which is our percent abundance. So to accomplish that, we hit the multiplication symbol, and then we hit 92.41, and then we divide by 100. Okay, and at the end of your first step, you should end up with a number around 6.47. Is everyone okay so far? These problems are particularly prone to calculator error, so it's really important that we enter it properly. Next, we're going to add this following calculation to our total. So to do that, we're going to hit the plus sign. We're going to hit the plus sign. One moment. And then we're going to hit parentheses, and you should see a 0 appear. We're now going to enter everything in this second portion of our calculations into our calculator. So we're going to start by entering 5.998 times 7.59, and then divided by 100. And at the end, when you push the equal sign, you should get a number close to 6.925. Does that match what you observe using your calculator? Okay, so let's enter in our final results into our report sheet. So we end up with a final average mass of 6.925 AMU. And the reason why we're only able to retain 4 sig figs is, well, actually, how many total sig figs are we allowed to report given our percent abundances? 3. So we're going to take this 925, we're going to look to the right, and we're going to round it to 6.93 AMU. And that would be a complete calculation for the average atomic mass of lithium. You can actually check your work if you pay attention to the periodic table and you go and find lithium in the periodic table. And if we zoom in really, really closely, what do we see is the average atomic mass of lithium? About 6.94, 6.93. Our calculated value is not going to exactly match because we're not recording our masses to the largest level of precision, nor are we recording our percent abundances to the largest level of precision. Does that make sense, everyone? How we calculate average atomic mass, and then most importantly, how you check your work. Okay. We're going to be doing a lot more calculations today involving percent abundance. I really wanted everyone to get a chance to try these problems on their own. We'll be having another quiz related to percent abundance and today's lecture topic. Does that make sense to everyone? Yes.
I have a question. So I don't put it all in the calculator at once. I do one step and then the other and then add those two.
That is perfectly fine. That is 100% okay. As long as you're retaining the maximum number of decimal places.
So that's what I did, and I get 3 decimal places rather than but it seems like over here it's 2 decimal places for the range.
Yes, and the reason why we have to round to 2 decimal places is looking at this multiplication operation, how many sig figs does this percentage have? So then that limits the number of decimal places in this answer, and in turn limits the number of sig figs you report to 3. Does that make sense? Okay. Let's now continue on and do a bit more practice on percent abundance calculations, and let's start to move into more advanced percent abundance calculations. So what we're going to do, if you're curious why we left this giant empty space in your notes, is we're going to show how to develop an equation to calculate the percent abundance of an isotope using the masses. So the main use of this equation is to find percent abundance given isotope mass. So let's start off with a simple premise. If we have only 2 isotopes, if we have an element with only 2 isotopes, so let's call this isotope 1, and let's use a different color for isotope number 2. Okay, so if we have these 2 isotopes and they each have a percent abundance. So let's suppose this is percent 1, which is the percent abundance. Okay, and isotope, each of these isotopes has a percent abundance that we'll label percent 1 for isotope 1 and percent 2 for isotope 2. Now, if we add up each of these percent abundances, what will we get? 100%. So both of these abundances added together will give us 100%. And this is an important relationship for a 2-isotope system because we can say the percent abundance, let me use a different color pen for this. If we wanted to solve for the percent abundance of isotope number 1, the percent abundance of isotope 1 is equal to 100% minus the percent abundance of isotope 2. Okay, so that's the first relationship that we've established, just using algebra. Does that make sense to everyone? So we can write the percent abundance of one isotope in terms of the other isotope. Okay, now we're going to write out our average atomic mass equation. So if we have our average mass, our average atomic mass, it is going to be equal to the percentage of isotope 1 over 100 times the mass of isotope 1, which we'll call mass 1. Does that make sense to everyone? Do each of these variables make sense? What is this percent representing? Percent abundance, yep. And what is this mass representing? If I say mass 1, I'm describing the mass of the first isotope. Yeah. Okay. Plus the percent abundance of isotope 2 over 100 times the mass of isotope 2, right? So this is our average atomic mass equation. Now, suppose we know our average atomic mass. Why is that really easy to find? Is there a place that we can look up the average atomic mass whenever we want? Periodic table. So the average atomic mass is found from the periodic table. Each of the panes in the periodic table, the average atomic mass is the number below your atomic symbol. Okay, so we can easily get the average atomic mass, right? Now, suppose that we know each of our 2 isotope masses. So I'm going to put a check mark next to these. So suppose we're given each of our isotope masses. Those can be estimated using the mass number, but in general, you're going to want to look and you'll be given the exact mass of each isotope. Now, from this information, can we figure out the percent abundance? Can we calculate the percent abundance of each isotope? Do we have enough information? Although it looks like this equation is pretty complicated, although it looks like we have three unknowns, right? We don't know either percent abundance, right? Can we write out a percent abundance in terms of the other isotope? Are these 2% abundances related to each other? Yes. So what we're going to do is we're going to take this expression and plug it in for our percent abundance of isotope 1. And the reason why we're going through this derivation is because we're trying to generate a general solution. So for any system with 2 unique isotopes, we'll be able to, given the masses of each isotope and the average atomic mass, calculate the percent abundance of each isotope. That's our goal. We're using algebra, so we only have to solve this type of problem once. So let's plug in this expression and we'll get our average mass is equal to 100% minus the percentage of isotope 2 times, and let's use a different color, the mass of isotope 1 divided by 100. I'm going to abbreviate mass 1 as M1. Is everyone okay with that abbreviation change? Okay. And then, of course, this second portion of the equation just stays the same. The percentage 2 over 100 times M2. Now, if we know each of these masses, do we only really have one unknown? What thing do we not know in this equation? What do we not know? We know mass 1, we know mass 2, we know our average mass. What do we not know? Yep, we don't know the percent abundance of isotope 2. Can we solve this algebraically? Yep, and I'll show you each of the steps for how we solve this algebraically. So first things first, I'm going to multiply each side by 100%. Okay, so far, so good. Let me zoom in and let me adjust our view so we can better see this. Okay, perfect. So we have 100 times the average mass that I'm going to call M average is equal to 100%. And to make this expression a little bit easier to follow, what I'm going to do is I'm going to take this mass term and I'm going to distribute it to everything in our parentheses. So I'm going to take this mass term and I'm going to distribute it to these 2 terms in our parentheses. So we'd have 100% times what? M1, yeah, times the mass of isotope 1. So let's write that out. Minus the mass of isotope 1 times the percentage of isotope 2. Okay, so this equation is starting to look a little bit more simple. And again, we also have plus the mass of isotope 2 times the percentage of isotope 2. So we're already on the track to getting a reasonable solution, right? Is our percentage of isotope 2 getting more and more isolated? Yeah. So what we're next going to do is we're going to use a little bit of pattern recognition here. First things first, we need to move this 100% term to the left-hand side. So we're going to subtract 100% times M1 from both sides. Okay? So we have 100 times M average minus 100 times M1 is equal to. And now this is the part where we're going to get a little bit clever. Is everyone comfortable with how the left-hand side turned out? Does everyone see why when we move this to the left, we're subtracting it from both sides? That's why it's being subtracted on the left. Okay. Now, let's take a look at this right-hand term. Do we see %2 in both of our terms? Do we see %2 in both of our terms? Do both of our terms have %2 in them? Yes. So what we're going to do is we're going to factor out this term. So we're going to write out this expression as M2 minus M1 times %2. Okay. Now we're almost done. If we want to completely isolate this %2, can I divide by this entire term? Can I get rid of this term by dividing by it? Yep. So we're going to divide both sides by M2 minus M1. So this term cancels, and lo and behold, we have our %2 all on its lonesome. Does that make sense to everyone? So to write out our final version, of this equation in terms of %2, the percentage of isotope 2 is equal to 100% times, parentheses, the average atomic mass minus the mass of isotope 1 divided by the mass of isotope 2 minus the mass of isotope 1. So this is our way, given each component isotope mass and the average atomic mass, it allows us to calculate the % abundance of a single isotope. Does that derivation make sense? Did how we manipulate this equation make sense to everyone? At the very least, what I need you to be able to do, if you're going to memorize this equation, you're going to need to understand what each of the terms mean. This M average is the average atomic mass, M1 is isotope 1, M2 is isotope 2. Now you may ask, how do I pick isotope 1 or 2? It doesn't matter. As long as your labeling is consistent, this equation will work. Does that make sense to everyone? Okay. Now, there's another expression, there's another way of writing this. If we do the exact same derivation for isotope 1, we get a very similar equation. The only distinction being is that this time we're subtracting by the mass of isotope 2. Now, are these two percentages related to each other? What's true about both of these percent abundances? If we have two isotopes, they should add together to give us 100. So we have all the tools to calculate the percent abundance of each isotope, and we have the tools to check our work. So you should never be worried on an exam whether you've done the calculation correctly. You always have the tools to check your work. And that's why I like this method. Does that make sense to everyone? So let's put this into practice. Let's put this into practice. And one thing that I'd want you to consider and think about, and you'll see this on one of the more advanced homework assignments, is what happens if we have 3 isotopes? How do we deal with that? How do we calculate the percent abundance? And that'll be delved in more detail in the homework. So let's put this equation into practice now. Let's put this equation into practice now. And let's look at an actual problem that you see on a test or an exam. Carbon has an average atomic mass of 12.011 AMU. Okay? What is the average atomic mass? Is that needed for our calculations? Yep. So we'll label this as M average is equal to 12.011. Okay, carbon has 2 major isotopes. So let's label them using different colors. We have carbon 13. So C13. Do you want to call C13 isotope 1 or 2? It doesn't matter what you choose as long as you're consistent. 1, sure. Let's call this isotope number 1. So we know the mass of carbon 13 is equal to what? Do we know the mass? Yep, 13.003 AMU. Okay, let's now look at our second isotope. So isotope number 2 by default is going to be carbon 12, and the mass of this isotope, one moment, is equal to 12 AMU. Okay, now that we have both of our masses of each isotope, so this is mass 2, and we have the average atomic mass, let's write out our equation. So the percent abundance of isotope number 2 is equal to the average atomic mass minus the mass of isotope 1 times 100% divided by the mass. And now I'm going to go up and check my equation just to make sure I did this 100% correctly. The mass of 2 minus the mass of 1. So always make sure you're referencing your equation to check you have the right equation written. Okay, perfect. So here is our basic equation used to calculate the percent abundance of a single isotope. What is isotope 2 in this equation? What is isotope 2 representing? What did we label as isotope 2? C12. Okay, so what I'm going to do is I'm going to rephrase this as the percentage of carbon 12. Okay, that way I don't get confused. So now all I have to do is take this equation and plug in each of my numbers. So the percentage of carbon 12, do we know the average atomic mass? Yes, so let's plug that in red. So we have 12.011 AMU. Do we know the mass of isotope number 1? Do we know the mass of carbon 12? What is it? 12. Yep. So we're going to take 12 AMU times 100% divided by, oops, one moment. Do we know And we've, oh, yeah, that's an error. We should be subtracting by isotope 1, which is carbon 13, which is 13.003 AMU. Okay, on the bottom side, we plug in the mass of carbon 12, which is 12 AMU. And then finally, we subtract the mass of isotope 1. And what's isotope 1? What is isotope 1? Carbon 13, which is 13.003 AMU. Notice units of AMU cancel, and we end up with a unitless number. Let's now enter this into our calculator. And determine the percentage of carbon 12. So, first and foremost, we can enter in this top subtraction operation. So we're going to subtract these top two numbers. So in our calculator, we'll enter 12.011 minus 13.003. And you should end up with a negative number. That's normal. That's okay. Next, what are we multiplying by? 100. So let's multiply by 100. So times 100. Okay, we still have a negative number, negative 99.2. Everyone okay so far? Okay. Now what we're going to do is we're going to hit the division sign. We're going to hit the division symbol, which is right here. And then we're going to hit parentheses. Make sure you input the parentheses. And now what we're going to do is we're going to input this subtraction operation, still in our parentheses. So let's do just that. We're going to take 12 minus 13.003, and you should end up with negative 1.003. We're then going to hit the equal sign, and it will complete this division operation. So you should end up with 98.9 if you've done everything correctly in your calculator. Does that match? Okay. You really want to make sure you're comfortable entering these calculations in your calculator, as although this looks very straightforward, this is the #1 source of error in answering these questions. People just make a calculator error and their number ends up incorrect. So let's write down our percent abundance of carbon 12, which is, oops, one moment, there we go, which is 98.9%. Why is it flickering out? One moment. Let me close and reopen this. Give me one moment for that. So let's rewrite this. One moment. So let me rewrite our work so far in Scratch, just so that way we can see what we've done so far. So we've established, just as an overview, the average atomic mass is 12.011 AMU. The mass of isotope 1 was 13.003 AMU, and the mass of isotope 2 was 12 AMU. We then utilized our equation to calculate the percentage of isotope 2 by taking our average atomic mass minus the percentage of isotope 1 times 100 divided by the mass of isotope 2 minus the mass of isotope 1. We then plugged in each of our numbers. So we've established carbon 13 as isotope 1 and carbon 12 as isotope number 2. We then plugged in our average atomic mass, which is 12.011 AMU, the percentage of isotope, the mass of isotope 1. The mass of isotope 1 was 13.003 AMU. The mass of isotope 2 is 12 AMU. And again, the mass of isotope 1 is 13.003 AMU. Then times 100%. When we punch this into our calculator, following this by step, we got the percentage of isotope 2 was 98.9%. So that's our overview of what we've done so far. Do we need to go through this equation again for isotope 1? No. Is there a simpler way? Can we, if we know the percentage of isotope 2 and we know both of the percentages add to 100, can we calculate the percentage of isotope 1? Yes. So then the percentage of isotope 1 is equal to 100% minus the percentage of isotope 2. So that gives us the percentage of isotope 1, let's zoom in for this, is equal to 100% minus 98.9%, which gives us a measly percentage of 1.1%. Now, does this make sense? When we talked about carbon, what is the major isotope in this case? So if we said isotope 2, which is carbon 12, is 98.9% of all the carbon atoms in our universe. So which isotope is most prevalent in nature? Carbon 12 or carbon 13? 12. Carbon 12 is the more abundant isotope. Significantly so. Does that make sense to everyone? What we're going to have you do now is we're going to have you practice these examples using homework problems. And in the last block of class, what we're going to do is we're going to talk about fundamental laws of chemical reactivity and chemical composition, known as conservation of mass and the law of multiple proportions. So let's talk a little bit about the law of conservation of mass, and let's delve into detail into the key features and how we can utilize this law in solving chemical problems. Yes?
I did have a question.
Oh, yes. Allow me to go up. Yep.
So concerning sig figs, the lowest sig fig number is 2.
Yes.
Answer has 3.
Yes, so this is a unique quirk with specifically the mass of carbon 12. Because the mass of the carbon 12 nucleus is used as a standard for the AMU, it has more sig figs than, has so many sig figs that it's functionally considered exact.
Okay.
Yeah, and that's a unique quirk of the fact that an AMU is derived from the mass of the carbon 12 nucleus. It's actually used as a standard.
All right.
Does that make sense? Yeah. So, in the law of conservation of mass, it follows this general framework. First and foremost, atoms cannot be created or destroyed in chemical reactions. So, for example, if we take hydrogen, which is H2, and we react it with oxygen, which is O2, we can make potentially hydrogen peroxide. The key feature of this chemical reaction, the key feature of all chemical reactions, have we changed the number of atoms of each element? Have they changed? No. Atoms cannot be created or destroyed, and the number of atoms of each element before and after a reaction does not change. By this same notion, if atoms are composed of fundamental particles, so if we take a look at a hydrogen atom, we see we have a proton and an electron. If the atoms themselves, if the number of atoms does not change, does the number of particles also remain constant throughout? Yes, atoms are made of these particles. If the atoms aren't changing, these particles aren't changing in amount. Okay, this is really important, and I just want you to underline this. When you think about subatomic particles, they do not change during a chemical reaction, and you really just want to think about this for electrons. There are reactions later on in this class that involve the transfer of electrons, and I just always want you to keep in the back of your mind, the total amount of electrons is not changing. Now, atoms have mass, right? We've calculated the isotope mass, which is the mass of a specific atom of a given isotope of an element. And we know that each of these atoms that we've drawn has a mass, right? Since atoms have mass and the number of atoms are not changing, will the mass also not change? Let's go through this one more time. Atoms have mass, right? So if I put, for example, all of my atoms on a scale, if I put all of my hydrogen and oxygen atoms on a scale, I would get roughly 34 AMU. If I start with 2 hydrogen atoms and 2 oxygen atoms, and I end with 2 hydrogen atoms and 2 oxygen atoms, if my number of atoms does not change, will I expect my mass, if I put all these atoms on a scale, to change? No. So that's 34 AMU. The exact number doesn't matter. The key principle I just want you to keep in mind, since atoms have mass and the number of atoms does not change, the total mass before and after a reaction does not change. Mass is conserved during reactions. So how can we see this at a macro scale? We aren't able to look in and see the individual atoms and particles, but what we are able to do is run a lot of chemical reactions. So let's zoom in a little bit here. So from a macro scale perspective, suppose you wanted to react sodium and chlorine to make sodium chloride, okay? So in this process, we're taking 7.7 grams of sodium and reacting it with 11.9 grams of chlorine. Now, at the end of this process, we isolate, or we attempt to isolate, very close to 19.6 grams of sodium chloride. This, of course, is an extraordinarily efficient and high-yielding reaction, so we can really start to see and observe conservation of mass in practice. So if you mix this sodium solid and chlorine gas in a sealed container, and you record the mass before they react. So our initial mass is 19.6 grams. Following the idea of conservation of mass, what total mass will we have at the end of this reaction? Yep, 19.6. The mass before and after the reaction does not change. Mass is conserved. And that's because all of these atoms that react, the total number of atoms does not change before and after a reaction. Now, one critical point that I want you to keep in mind when we look at our labels for each of these masses, even though our total mass is unchanged, is the chemical composition of that mass different? Does sodium have the same property and reactivity as sodium chloride? No, they have different properties and reactivity. Mass is conserved, but we have changed the chemical identity of our, as we go from reactants to products. Okay, so we can get really clever with conservation of mass in later problems. But just remember, mass is conserved in a chemical reaction. So if we want to look at conservation of mass from a micro scale perspective, we've done this example previously with hydrogen peroxide. Let's do this example again, this time with water. How many hydrogen atoms, how many white spheres do we start off with? 4. And how many do we end with? 4. How many oxygen atoms do we start with? How many red spheres? How many do we end with? 2. Okay, mass is conserved. If we use average atomic masses, considering hydrogen is 1 AMU, and we have 4 hydrogen atoms, we have a mass of about 4 AMU. Let's do the same thing for oxygen. So looking at these oxygen atoms, if we go to our periodic table, just to estimate here, and we go and try and read the number straight below oxygen, what is oxygen's atomic mass about? 16. Okay, so we know that an individual oxygen atom, on average, in aggregate, has a mass of about 16 AMU. We have 2 oxygen atoms, so that gives us 32 AMU. Now, without doing any calculations, what I'd like you to tell me is, what is the total mass of water that we generate? The total mass of both of these water molecules, just using conservation of mass. Would anyone like to volunteer? What was that?
36.
36, exactly. If the mass before and after a chemical reaction doesn't change, to figure out the mass of water that we expect to generate, we just add up the mass of each of our reactants. So 4 plus 32 gives us 36 AMUs of water. So it's a really powerful principle that really underpins chemical reactions. Does that make sense to everyone? Okay. Now, as part of our empirical studies of different compounds, we've also developed, and this law was put forward, as the law of definite proportions. And this is a really powerful law. It's really our first attempt at starting to explain chemical composition and explain patterns of chemical reactivity. So what this law says, the law of definite proportions, compounds have a definite fixed number of atoms of each element. So for example, HCl. How many hydrogens do we see in HCl? How many H symbols do we see? 1. So we have 1 hydrogen. And how many chlorines do we see? 1. Okay, we have a fixed, definite number of atoms of each element, right? As we've discussed earlier, is there such thing as half an atom? No. So we can only really count atoms as whole number quantities. Now, as an elaboration on this, each unique compound has a specific fixed whole number ratio of atoms. Okay? So if a compound's unique, it has a unique number of atoms of each element. And importantly, all samples of the same compound have the same number of atoms of each element in their formula and structure. So let's showcase how this works. So if we're looking at H2O, for example, your stereotypical water molecule, drawing it out, we have how many hydrogen atoms? How many H symbols do we see? 2. So we have 2 hydrogens, and how many oxygens? 1 oxygen. Now, looking at another compound, H2O2, and let's break out a different color for that, just to showcase the difference. H2O2. In this case, we have how many hydrogens?
2.
2, yep. And how many oxygens do we have?
2.
2. So then, because we have different numbers of atoms of each element, are these different compounds?
Yes.
Yes, right? By definition, if the number of atoms of each element are different, they will be different compounds. Now, and this is a really interesting part of this law. Suppose we have a mystery compound. Suppose we're analyzing a mystery compound. And we know that it has one hydrogen atom and one oxygen. Let me rephrase this. It has 2 hydrogen atoms and 1 oxygen atom in its chemical formula. We figured out using the masses of each element in this compound. Based on the atoms of each element, which compound is this mystery compound? What compound does this mystery compound match? Water, right? They have the same number of atoms of each element. Ergo, we can assign this mystery compound or this unassigned compound as water. So this is how we can identify unknown samples as a given compound. We look at the amount of each element in that compound, and then by comparison, we can then say, oh, this unknown has the same ratio of atoms of each element, the same mass ratio of each element. Ergo, these two are the same chemical species. It's long, grueling work, but that's how a lot of new compounds were identified empirically. Okay, so again, just to stress, unique compounds have a unique ratio of atoms of each element according to this law. Now, we're going to take this idea and expand it. So the next major elaboration of this law is the idea that all samples of the same compound will have the same number of atoms of each element. Okay? Now, if they have the same number of atoms of each element, for example, in H2O, we have 2 hydrogens and 1 oxygen, right? Does this also mean if we look at the number of atoms of each element, would the ratio also be the same? Would the ratio of hydrogen to oxygen atoms also be the same? Yes. So then, samples of a compound should have the same ratio of atoms of each element. So then, we know that for water, there are 2 hydrogen atoms per every 1 oxygen atom. And let me make this, there we go. Okay. So then, if this ratio is fixed for a unique compound, let's say now we're looking at a large number of molecules of a compound. No matter the amount of water molecules we have, we know for every single water molecule, what's the ratio? 2 hydrogens per 1 oxygen, right? Now, because of that, the ratio of atoms of each element will always be the same if we're dealing with the same molecule. It doesn't matter whether we're counting 1 water molecule or 1,000,000 water molecules. They have the same formula and the same ratio of elements. Now, and let's now put this all together, and let's draw out our water molecule that we've been focusing on. Let's draw it out in a different location. One moment. So, suppose we're looking at 1 water molecule. we have 2 hydrogens per every 1 oxygen. If we look at, for example, 6.02 times 10 to the 23rd water molecules, even though we have substantially more water molecules, so we'd have 2 times 6.02 times 10 to the 23rd hydrogen, and 1 times 6.02 times 10 to the 23rd oxygen. Oops, one moment. Now, even though we're looking at a larger number of atoms, as we see, the ratio is still the same, still 2 to 1. Now, since atoms have mass, right? These atoms have mass. We can rewrite this atom ratio into a mass ratio. One moment. There we go. So then we can say we have 2 AMUs of hydrogen per every 16 AMUs of oxygen. And just like the atom ratio is fixed, is the mass ratio also fixed for a unique compound? Yes. Okay. So then the ratio of masses of each atom of each element will remain constant, no matter the size of your sample, right? So then we can scale this up even further. So let's suppose we're looking at a drop of water. Let's suppose we're looking at a drop of water. And suppose there are 2 milligrams of hydrogen per every 16 milligrams of oxygen. Okay, same mass ratio, right? We develop this mass ratio from our molecule. It's the same when we look at groups of molecules, right? Now let's suppose we're studying a giant cup full of water. We're studying a large sample of water. If this liquid is water, fundamentally, what will the mass ratio be? Same, 2 to 16. So for example, it could be 2 kilograms of hydrogen in this water sample per every 16 kilograms of oxygen. This is really, really useful and really powerful, as it means that we can study any size sample of a compound, and from that, if we can identify the ratio, the mass ratio of each element, we can identify that compound and compare 2 chemical species and say whether they're the same compound or different compounds. Does that make sense? Okay. So it doesn't matter the size of the system you're looking at. If it's the same compound, it'll have the same mass ratio. Now, we can get even more clever with this, and this is the last topic we'll discuss before the end of the period. And this involves invoking the law of definite proportions. And the law of definite proportions is concerned with comparing compounds and reactions. Compounds using chemical reactions. Okay, so for the law of definite proportions, we know all samples of the same compound must have the same ratio of masses of their constituent elements. Okay, so for example, carbon monoxide has 12 AMUs of carbon per 16 AMUs of oxygen. As long as we're dealing with the same compound, we have the same mass ratio. That's just our summary for that. Now, there's one little caveat I need to discuss when we talk about mass ratios. So, in the law of definite proportions, if it's the same compound, they will supposedly have the same ratio of masses of their constituent elements. Now, the book that you're using and the law of definite proportions often is describing not the absolute chemical formula, but what's known as the empirical formula ratio. And so a better way of rephrasing this law in order to be more useful in later sections of the class is that all samples of the same compound will have identical empirical formulas. And you may ask, what is the empirical formula? Well, the empirical formula is the smallest ratio of atoms of each element. So since this law deals with atom ratios, we are really talking about empirical formulas, the simplest ratio of atoms. So let's show why this is important to draw this distinction. Let's show why this distinction is relevant. Suppose we're looking at NO2. NO2. So we have nitrogen and 2 oxygens. So just to write out our atom ratio, how many oxygens do we have? 2. How many nitrogens do we have? 1. Okay, perfect. So this is our ratio. Now, let's look at an example that throws a wrench into the works. If we look at N2O4, so drawing out N2O4, we have how many, whoops, one more. So how many oxygens do we have? 4, yep. And how many nitrogens do we have? 2. Now, clearly, are these 2 species different compounds? Do they have a different number of atoms of each element? Yeah. However, if we're only looking at atom ratios and mass ratios, this ratio simplifies to 2 oxygen per every 1 nitrogen. Right? Do you see how the atom ratios are the same? So these types of compounds with the same ratio of atoms, what we say is that they have the same empirical formula, required a bit more work to distinguish. The reason why I'm showcasing you this example is because there have been cases when chemists were attempting to differentiate various chemical species using mass ratios. That, for example, let's look at a mystery compound. Let's look at a mystery compound to drive home this point. Let's suppose we have a mystery compound X. And from our studies, we found it has 2 oxygens per every 1 nitrogen atom, just using our mass ratios. Would we be able to distinguish and assign X solely using these atom and mass ratios of each element? Can we say that X is definitively one of these 2 if all we have is a ratio? So do these 2 compounds have the same ratio of elements? Yes. So can we distinguish them solely using this ratio? No. And that's the critical point. The law of multiple proportions works for most compounds, except for those with the same ratio of elements, the same empirical formula. So there are methods to distinguish X apart, and there are methods to tell apart these 2 compounds, and we'll talk about that in chapter 3, how we distinguish different compounds using other properties and other characteristics. So that's all we have for today. We'll do a lot of practice examples, and if we have some time, we'll be able to do a little bit of lecturing in lab.